This is now the third computer session where we're going to add a perfectly absorbing boundary condition. In front of us, we have the code from the second session. Let's run this and remind us what happens. So we injected a simple Gaussian source at the middle of the grid that propagated in either direction. And what we see when that hits the edge of the grid, it reflects. Well, suppose we had a device in the middle of our grid that we're simulating, and we want to know how much of the pulse reflects off of the device. How do we tell the difference between what reflected from the device and what reflected from the edge of our grid? And the reality is, I don't think we can. So we need to do something at the edges of our grid. We want this pulse, when it hits the edge of the grid, to just look like it keeps going and disappears and does not reflect back in. And in a one-dimensional code, it turns out we can do this just about perfectly. We call that the perfectly absorbing boundary condition. So let's get started, and let's save this as a step 3, our new code. And our comment here, rather than add a simple Gaussian soft source, we've already done that, add a perfectly absorbing boundary condition. This will be a very short computer session because there's not much we need to do here. So the next section, everything stays the same. The next section where we need to add things is where we're initializing our parameters right before the finite difference time domain loop. And remember, to do this boundary condition, my assumption is that you've watched the theory slides, because I'm not going to explain the theory. And this in particular will seem rather strange if you haven't looked at that. So remember, to do this, we've set our time steps so that the wave travels one grid cell in exactly 2 time clicks. So in order to do this perfectly absorbing boundary condition, we need to know what the field value is outside of the grid. And we do that by storing the field value at the edge of the grid for 2 time steps and then using that value. So that's what these boundary terms are doing. So we do that for the magnetic field and the electric field. And everything always starts at 0 in finite difference time domain. So our boundary terms now start at 0. So that's it. Now we have to go into the main finite difference time domain loop and do some modifications there. So right after we update the H field from the E field, at this point in the code, we have an updated H field. So what we'll do now is record the value of H, which is at the edge of the grid, and we will record that for 2 time steps. Record H field at boundary. And we'll say H3 equals H2, H2 equals H1, and H1 is the field at the first step. Now, the order this is happening is very important. We would not put this statement first, this statement second, and this statement third. They have to happen in this order so that H3 is Hx at point 1 2 time steps ago. And we'll use this as the H value outside of the grid. Okay, we're going to do the same exact thing after we update the E field from the H field. Record E field at boundary. And this looks very similar. E3 equals E2, E2 equals E1, and E1 is EY at point NZ. Now, the reason we record HX at the first point and EY at the last point has to do with the staggering of the E grid. We just happen to have, updating the H field, we have a boundary condition at one side of the grid. Updating the E field, we have a boundary condition at the other side of the grid. After having done this, E3 will be EY at the last point in the grid 2 time steps ago. And we can use that to replace our Dirichlet boundary conditions. So let's go ahead and do that. Let's go back up and look at where we put our Dirichlet boundary condition. This is what's causing it to reflect. Remember what we needed here. we needed an EY at big NZ plus 1. But this value doesn't exist outside of the grid. However, we really just calculated it, E3. So let's put E3 in its place. Likewise, down here, we used to have an HX at 0.0. This doesn't exist. However, we really just calculated it with H3. So we can put H3 in its place. And that's the perfectly absorbing boundary condition. Let's run it and watch what it does. Now, it looks like something has reflected, but notice the amplitudes up here. It's 10 to the minus 3. So every reflection, we go down about 2 orders of magnitude. That means that something is reflecting. Why is something reflecting? Let's look at that, and then we'll know how to make it a little bit better. When we calculated our time step, we assumed that the speed of the wave is and the speed in the grid are the same, that the speed of the physical wave and the speed in the grid are exactly the same. And we showed last computer session that's not necessarily the case. There's dispersion. A wave in a finite difference time domain grid actually travels a tiny bit slower. So if we wanted to reduce the amount of reflections at the boundary, well, an easy thing we can do is increase the grid resolution. Now there's less dispersion, and what we'll see is less reflection at the boundaries. Notice now we're 10 to the minus 4, and we just improved that by an order of magnitude. So the only reason it looks like something is happening here is because we're constantly scaling the amplitude so we can see the noise. And what if we did n lam of 40? So we're now using a grid resolution of lambda over 40. Notice it's taking longer to run. Let's look at what gets reflected back. 10 to the minus 4. So that didn't help much compared to the n lam of 20, but there was a big difference between n lam of 20 and n lam of 10. And now we're just seeing a lot of noise. You see all the ripples. Our amplitude's down 10 to the minus 11. So I guess we call this perfect. It's not quite perfect, but it is extremely good. Our reflection is down 10 to the minus 4. So that's something like 0.01% reflection. That's it. That is the perfectly absorbing boundary condition. Thank you.